Okay, thank you for the introduction. You said something about what's not in the title. I want to start with the question. You must, if you read the title, there's a question what means Javal typings and what means Java Lambda. These two questions I will answer in my talk. First, have a look at the overview, at the outline. I begin with the introduction. Then, okay, you said it. Type inference is a topic of my talk. And finally, I will show the implementation in Haskell. Let's have a look a little bit in the history of Java. Functional features went into Java, I say. The first ideas are given in 1997. It was an idea, an implementation of Pizza. Java was extended to Pizza by abstract data types, by parametric polymorphism, by higher order functions. 1 year later, they reduced only to parametric polymorphism. They called it JG, generic Java. Then, 7 years later, in the standard of Java 5, Oracle, or I think it was Sun, integrated generics. Generics are a special form of parametric polymorphism, and there was a problem. The problem of the soundness of the type system. That's the reason why they integrated wildcards. Wildcards are a restricted form of existential types. And now, in this year or in the next year, in Java 8, they want to introduce lambda expressions, or they call it clones. But I would say in the world of the functional programming, clones are implementation technique, so I will speak about lambda expressions. But there's one feature which is not introduced, and this is the type inference. Only local type inference. Local type inference means that parameter types of lambda expression could be inferred, but not the whole type of the lambda expressions. So this is the topic of my talk. First, have a look at the language Java Lambda. The language Java Lambda takes the standard of Java 5.0 and is extended by lambda expressions. The lambda expressions are written like this. It's for the lambda as a sharp used, and then the brackets and so on. Then we have function types, and the function types are written like this. Here are the argument types, and here's the result type. And we have a possibility to evaluate a lambda expression, and the evaluation operator is the dot, like this. The syntax is oriented at the idea of Mark Reynolds in his paper project Lambda, the Java language specification 2 years ago. The problem is that Mark Reynolds is not the manager in the moment for Java, and Brian Götz decided to use not function types. They integrated the lambda expressions into something which they call functional interfaces. So we have not really function types in future in Java 8. But my standard, I think it would be good to have function types. There are some reasons. But the problem is that some Java code is unreadable. That's the main argument why they use the interfaces. And I say, you're right, but you can use type inference, then you need not to write down the unreadable function types. Okay, that's my idea. Let's have a look at an example. This is a very simple example. I say a matrix is an extension of vector of integer. And I have an operation. The operation has 2 arguments. The first argument is a matrix, and the second argument is a function which is applied to its own, to this object, and to the first argument. Yeah. Okay, you can apply this, and in a main function we have 2 matrices. And we have the first matrix applied to the operation function, and the first argument is the second matrix, and the second argument is the matrix multiplication written in the lambda style. I have that here. screw is leaved out. I think any knows how to implement matrix multiplication. Okay, that's an example, and our goal is to write it like this. You need not to give type informations here in the front for the function op, and also not for the arguments. That's the idea, that you could write Java like this, and the system infers the types automatically. Okay, I look back in the old time which type inference algorithm exists, and I found one type inference algorithm from 88 from Fu and Mishra, and they had a very similar situation to the Java with lambdas. They had a small language, lambda expressions with the subtypings, and gives therefore type inference algorithm. So my idea was to adapt this type inference algorithm to Java. Okay, the type inference algorithm, they call it W type, which means well typing. That's the title of my talk. And the W type algorithm has two inputs. It has an input, a set of type assumptions and a lambda expression, or an expression, not necessarily a lambda expression. And the output is a well typing for the input expression. And the well typing is a judgment like this. You have a set of coercions. Coercions means set of subtype pair. You can say they are constraints. And you have a set of assumptions. And if you have these two, you can follow that the expression n has the type t. That's the idea. And we adopt this algorithm to Java. Okay, the algorithm consists of three subfunctions. The first subfunction is called in the original type. I call the type class. The second one is called match. It's the same. And the third one is a function which they call consistent. And it's not a very good function because the result is not that what we want. The result is such that there is only one judgment, okay, but the judgment says not many. So I changed it to an algorithm which I give some years ago, type unify, and so I get more information. We will see later. Okay, the first function is the type function. The type function maps a fresh type variable to each subterm of the function. It determines result types. These result types are type variables for each function, and it determines the corresponding coercions, the subtype pairs. Then the second function is the match function. The match function uses the coercions, the atomic coercions, which means they eliminate the function type constructors. And the second one is the type unify algorithm. The type unify algorithm takes a set of atomic coercions, and the result is a set of substitutions and a rest set of atomic coercion sets. I give here the condition. The condition is that each substitution, which is the result of the algorithm, applied to the input, leads to correct subtyping pairs. The problem is that there is a rest of coercions which cannot be solved. This is not very problematic, but the reason is that there is no other conditions. That are, you can say it's something like free type variables with a condition. Okay. And the whole algorithm looks like this. We give input is a set of type assumptions, like in the original, and the second input is a class, and the result is a set of well typings and fail if there is no correct typing. And the algorithm looks like this. The function type gives as result type variables for the given functions and a set of coercions. And this is the input of the match. The result of match is one substitution and the set of atomic coercions. And the this result of these atomic coercions are the input of the type unify, and the result of the type unify, as seen on the last slide, is a set of substitutions and the rest set of atomic coercions. And then the result is we apply these two substitutions to the type variable of the function, and we get a possible type of the function. Okay, that's the idea of the algorithm. And now let's have a look at the implementation in Haskell. I do this in 4 steps. First, I show the abstract syntax. It's, I think, a straightforward implementation. The class has a name. The class has a list of other classes which are extended or implements. The class has an instant declaration, and the class has function declarations. You see there are no methods because because you can all do with function declarations in the moment. And the function declaration is the name of the function and then maybe a type. You can give the type, but you must, it's not necessary to give the type, and an expression. And interesting is the data expression, that's okay, the lambda and so on, the normal expressions of Java. And then we have an additional expression, the type expression, where we can type each sub-expression in the data structure. And last, very interesting, is the lambda body could either be a statement or an expression. This is a definition in Java. In the running of functional programming, you would say a statement is also an expression, and then it's no problem. Okay, the function type is implemented with the state monad. The state monad is given there. The state is the set of type assumption and the int variable. The int is the number of the free type variable, and the result of the monad is the pair coercion set and class. Now the class is a typed class with the type variables. Okay, the implementation is done like this. First, I have to filter the expressions of the function declarations, and then I call the function type expression list. You see, the function type class is separated in function for each arc of expressions which we have. Then we have given like this. First, in the type expression list, I determine the type of the expression, and then with the bind operation, I do the rest of the list. I think it's straightforward, and at the end, I give the type expression, only the type declaration for the function, and you see here the result type is also a coercion set, but here it is only an expression and not an expression list like here, and a class like in the first function. Okay, let's have a look at our example, and I have implemented it in Haskell. You can see it here. So, okay. I hope it's not too small. You can see here the class matrix, okay. And then here the operation, and all sub expression has now a type variable given as type. And you have here a set of coercions where you can see there are function types inside and there are fresh type variables. Let's have a look. There is a type constructor matrix. This is the type of this, and so on. This is the first step of the algorithm. Okay. The next one is the match function. For the match function, I need two data structures. The first data structure is a substitution. It's a okay. It's a result, and I have a second one. It's equivalent types. This is necessary for the occur check from the unification. Okay, I have to make a little quicker. You can see the result of our of the type expression. and we can show the result of the next step of the algorithm. It's the match, and you can see here now the the syntax function types are included, which means that the type variables are substituted by function types, and the set of coercions are only atomic coercions. There is no type constructor at all in this set. That's the second part, and now we come to the type unify. The type unify, as said before, as an input and a set of atomic coercions, and the result is a list of substitutions and a subset of atomic coercions which are not unified. We will also look at this in our example. Here, the result of the match function, we can look here with the whole compile function, and now we see that we get more than one substitution. These substitutions are given here. You can see here is the first one to this, and the second one from here to where it is here to this, and you can see there five different substitutions. This is the problem that the type unify algorithm is not unitary, but it's finitary. You can get more than one correct typing. That's the problem. You can see it in the substituted results of the typed functions. You can see that we have 5 correct typings for this untyped given Java program. Okay, and now the question is how to handle with this. You can do, the first one is the problem of the remaining coercions. The remaining coercions look like this. You have only type variables, and there is a condition between this. You can say, okay, all type variables which are given in the type of the function, you can set equal. Then it's like this, and then you can get a correct Java program. It's possible in Java to give parameters of operations, and you can say, okay, we do an equation between these two type variables, and we do it here like this, and say, okay, that's a correct Java program. This is not a very good idea because it's not a principal type. The problem is it would be correct to substitute these two type variables with different types. The only condition is that the different type must be in a subtype relationship. And though another idea is you can use in Java something like this. You can give bounds of the parameters of functions. Okay, you can solve this problem if you use a bound like this. You can say this type variable must be a subtype, an extent of this type variable. The problem is in Java it is not allowed to use here bounds in the moment. You can type variables, you can use only real types. But I think it would be no problem to change a little the Java at this position to introduce bounds of type variables. Okay, I came to the conclusion. My conclusion, I've showed that the Fufu and Bishop type instance algorithm can be adopted to Java Lambda. The algorithm can be improved by introducing of type unification. I've done this, and the prototype implementation is done in Haskell. Future work, as I said before, an extension of Java is necessary such that bounded type variables are allowed as parameters. Then the next idea is to do an IDE like Eclipse, such that the programmer can select the type. If there are more than one type, the programmer can select which type he wants. Or the other idea is to introduce intersection types to Java, which means that all types are correct. And then we must a little bit change the code generation, though there is a dynamic binding. If the one type, if the argument, if the function is executed, If the one type is given, then the one code must be executed, and if the other type is given, the other code must execute it. And yes, that's it. And the last one, which I have never considered in this paper, is overloading. In Java, it's possible to give overloading. If I allow overloading, you get much more correct types from the unification. It's not very good. It's not a little bit difficult to handle with this. So I've restricted and I've given the overloading. I have an idea how could it be done, but it's future work. Okay, that's it. Thank you.
Yeah, we have some time for questions.
So I must have missed, what do you do with the type that if the user does give you a type before you do the type inference? Do you still do the type inference and then do some checking that this type is correct?
If
I missed that.
Okay, you can do it. It's in the data structure there may be. If you if there is a type given, sorry, where was it? Here. Here's right. Maybe. If a type is given from the user, then maybe it's a type, and if the type is not given, then at this position is nothing.
So do you do anything with this type?
Yes, it's an assumption for the input of the algorithm.
Okay.
Does your system deal with arrays?
Sorry?
Does your system deal does your system handle arrays? Java arrays? Arrays. Sorry for me.
I saw arrays. No. Okay. It's not really correct. What I have said. Not the base is not the whole Java 5. It's in the moment we have done no arrays because the vector can be used as a form of arrays. There's some problems in Java with arrays because of the soundness and so on, and that's the reason why in the moment we don't use arrays.
In your small example, you had a lot of subtyping relationships, and I think that's quite typical because probably for every application you generate subtype constraints. Don't you think that's a problem with usability? Because if the user has presented sort of 5 different val typings, so which of those should he choose?
Okay, yes, it's an interesting question, and I've had enough time to explain that in real we have only 2 in this case. There are 5 because many internal type variables are different. You can filter these only in the result in this case would only that there are only 2. And if you look at these 2, you can see that really it's only 1 because the second one is a subtype, but the implementation of the subtype is the same as of the supertype. So I would say I have to do something to filter the real different types, I would say. And then I think you can handle it. I hope.
Okay, I think we have to stop here. Let's thank the speaker again.